Hello again. In the second part, we'll continue to describe the refining processes. First, I will show you the second objective of a refinery. Then we'll study together some important refining unit. And finally, we'll conclude by the description of a typical refining diagram. We finished the previous video by discussing the first objective of a refinery, to transform crude oil into different products following commercial specifications. We already seen two types of units, the CDU and the VDU, for the separation of the different cuts by distillation. And then HDS, amine and reforming units in order to improve the quality of the final products. The yield we can obtain from crude oil depends on the origin of the crude. For instance, for an Arabian light crude from Saudi Arabia, we have at the outlet of the crude distillation unit 5% of gas, 20% of gasoline, 30% of kerosene and diesel, and 45% of heavy cuts. But these yields obtained at the outlet of the CDU do not correspond to the market demand for final products. If we compare the crude yields and the final market demands, we can observe that we have a lack of diesel, jet fuel and gasoline, and a large excess of heavy products. Let's see now how a refinery can solve this problem and try to match the market demands. The idea is to transform the heavy products recovered at the bottom of the CDU in lighter products according to the market demand. For that, we feed the VDU with atmospheric residue. By doing that, we recover vacuum distillates with carbon number between 25 and 50. And at the bottom, a vacuum residue with a carbon number higher than 50. The vacuum distillate is treated in a fluid catalytic cracker, or FCC, or a distillate hydrocracker called DHC. The vacuum residue will be treated in a delayed coker. We'll see later in detail the objectives of these units. But for the moment, just remember that the basic objective is to cut the long chains into smaller ones. In conclusion, the idea is to transform heavy cuts into diesel, kerosene, gasoline as needed by the market in order to balance the offer and the demand. In conclusion, we can list three main refinery objectives. First, to separate the crude in the distillation column into different petroleum cuts. Second, to improve the quality of these cuts in order to meet the commercial specification. And third, to improve the quantity as requested on the market. FCC, DHC and delayed coker units are able to change the yields of products by transforming heavy products into lighter ones, such as gasoline, kerosene and diesel oil. Let's now go deeper into the different units of the refinery. We'll start with the gas treatment. Gases are obtained at the top of the crude distillation unit. Then they are split again in other distillation columns called a gas plant. To obtain first fuel gas is used as internal fuel in all the furnaces of the refinery. We also obtain propane and butane as final products. But it is mandatory to eliminate sulfur components which are present in these cuts. One of the most important components is named H2S. This H2S is eliminated in an amine unit. Let's have a look inside an amine unit. The gas containing H2S is put in contact with a chemical reactant, an amine called DEA. A chemical reaction occurs between the H2S and the DEA. The sweet gas goes to the outlet of the column and the spent amine goes to the regeneration column. This unit is also largely used for natural gas treatment. You will study this more in detail with Olivier during the next video. After the gas, we have the naphtha cut. This cut is one of the main feeds of the petrochemical industry. In general, this cut is directly sent to the petrochemical plant. On the diesel cut, depending on the origin of the crude, the cetane number obtained is high enough to be within the specification. It's the same for the coal flow properties, but the sulfur content of the diesel cut from the crude distillation is too high to meet the target specification. So, to decrease the sulfur content below 10 ppm weight to comply with European specifications, we need to treat this cut in a unit called the hydrodesulfurization unit, or HDS. At the outlet of the HDS unit, the diesel fuel complies with specifications such as density, cetane number, coal flow properties, and sulfur content. The diesel can be stored in the final product tank, ready to be sold to customers of the refinery. Let's have a look now at the chemical reactions. which take place inside the HDS unit. The desulfurization reaction takes place inside the reactor, filled with catalyst. Catalyst is a solid compound designed to facilitate and accelerate the chemical reactions. The hydrocarbons containing the sulfur molecules react at the surface of the catalyst with hydrogen molecules in gas form. At the end, the reaction we obtain on one hand hydrocarbon without sulfur, on the other hand H2S, hydrogen sulfide, which is the product of the reaction between sulfur and hydrogen. We need a high enough temperature to activate the reactions. Typically the temperature inside the reactor is between 360 and 400 degrees C. We also need enough hydrogen pressure to help the hydrogen molecule go inside the catalyst and react with the sulfur molecule. Typically the pressure of diesel HDS is between 40 and 80 bars. Now, this was for the diesel cut. Let's do the same for the gasoline cut. Remember that the main specification to comply with is density, volatility, sulfur content and run. Density and volatility are regulated by operating the distillation column. The sulfur content is higher than the European specification of 10 ppm weight, and typically the run of this cut is really too low, in the range of 20 to 50. To decrease the sulfur content of the gasoline cut, we install another HDS unit. At the outlet of the HDS unit, sulfur content targeted is 0 ppm weight, because sulfur is a poison of the catalyst for the reforming unit, and also to comply with the sulfur specification of the gasoline. But the research octane number, run, is still far below the 95 targeted in Europe. So, to increase the run, the gasoline is treated in a new unit called the reforming unit. At the outlet of the reforming unit, the gasoline is then within the specification in terms of density, volatility, run and sulfur content. The gasoline can then be stored in the gasoline final product tank. The chemical reaction takes place inside a reactor filled with another type of catalyst. The paraffins react to the surface of the catalyst and they are transformed into aromatics with production of hydrogen. The run increases because the run of aromatics is higher compared to the run of paraffins. Another type of reaction is the transformation of naphthene into aromatics with production of hydrogen again. You will see with Michel next week that aromatics are really important bases for the petrochemical industry. This reaction takes place at high temperature around 500 degrees C and at a pressure of around 20 bars. In addition, the hydrogen produced during these reactions in the reforming unit is directly used in the diesel, kerosene and gasoline HDS units. Until now we have seen the units which improve the quality of the products. Let's now discover the units which increase the quantity and the yield of the desired products. At the bottom of the CDU, the atmospheric residue is distilled under vacuum in the VDU to obtain vacuum distillate. The vacuum distillate is introduced into a fluid catalytic cracking unit called FCC. Let's have a look now at the chemical reactions which take place inside this FCC unit. The vacuum distillate is introduced at the bottom of the reactor in a big pipe called a riser. In the riser, the feed is in contact with a specific catalyst. The reaction occurs in the gas phase at higher temperatures. We recover the products of the reaction at the top of the reactor. The products of the reaction are separated in different cuts in a distillation column. The spent catalyst is recovered at the bottom of the reactor and is regenerated in a regenerator before coming back again at the inlet of the riser. The catalyst is circulated in the loop between the reactor and the regenerator. Catalyst is really specific. It looks like a very small round particles around 0.05 millimeter. This catalyst is so small that it's possible to fluidize it. To keep things simple, let's say that under some conditions it moves like a liquid. Look at this video, you will understand. The catalyst flows from the bottle to the glass like a real liquid. Under the operating conditions, the catalyst will break the long chain molecules into smaller ones. In this example, a C30 molecule is broken into a C10 and a C20 molecule. By doing so, we transform long molecules of the vacuum distillate into shorter ones. And finally, we produce additional gasoline and diesel fuel. We also obtain smaller molecules with double bonds, called olefins, like propylene. This molecule is really reactive and it is an important base for the petrochemical industry, for the manufacturers of plastics. In conclusion, we obtain at the outlet of the FCC a combination of different types of shorter molecules, mainly composed of aromatics and olefins. These reactions occur at high temperature, around 530 degrees C, and low pressure, around 2 bars. The vacuum distillate can also be treated in a distillate hydrocracker unit, called DHC. Let's have a look now at the chemical reactions which take place inside the DHC unit. The hydrocarbon molecules react at the surface of the catalyst with hydrogen. For example, aromatic molecules are saturated with hydrogen to form naphthenes. Naphthenes crack into linear compounds under higher pressure and high temperature. And long chain molecules can again be cracked into smaller molecules. Typical operating conditions are shown here. Temperature of the reactor is around 360 degrees and pressure around 180 bar. In conclusion, at the outlet of the DHC unit we obtain mainly diesel, jet and gasoline. Until now we have seen the treatment of the vacuum distillate. Let's see now what happens with the heaviest cut of the refinery, the vacuum residue, recovered at the bottom of the video. To convert the heavy residue, we can treat it in a delayed coker unit. The two main pieces of equipment in the delayed coker are the furnace and the coker drum. Notice that in this unit we have no catalytic reactor. Inside the tube of the furnace, the residue is heated to around 500 degrees C. At this temperature, the long chain molecules are firmly cracked into smaller molecules. The chemical reaction also gives aromatics, olefins, and a lot of solid coke, as around 30% of the feed of the unit is converted into solid coke. The coke accumulates very quickly in the drum, and thus it is necessary every 24 hours to remove the coke accumulated inside the drum. With specific equipment, using water injection at a very high pressure, around 300 bars, the coke produced in the drum can be sold and used for different applications depending on the coke quality. For example, to electrical power stations or for electrode manufacturing. In conclusion of this overview of the conversion units, I would like to summarize with you the 3 units we have just seen together that are able to convert heavy cuts into lighter cuts needed by the market. The yield of products obtained depends on the unit type. For FCC, we can obtain up to 50% of gasoline from the feed. The DHC is more adapted to produce diesel or jet A1. It's possible with a good catalyst selection to obtain more than 60% of diesel and kerosene. The delayed coker gives you an average 20% diesel and 10% of gasoline. In addition, it is important to remember that the FCC unit also gives you olefinic molecules like propylene, which are important for the petrochemical industry. Typically, the yield of propylene obtained is around 5% of the feed. To conclude, I would like to summarize with you what we have seen during these 2 lectures. The first step of a refinery is to cut the crude oil into different bases. This operation takes place in the crude distillation unit or CDU. All the cuts obtained at the outlet of the distillation column are not within the desired quality specification and need extra treatment in additional refining unit. The second step is to treat the cuts in order to comply with the specification and market demands. We have seen the HDS unit used to remove sulfur compounds from gasoline, kerosene and diesel, and the reforming unit to increase the run of the gasoline. We added the FCC, which treats the vacuum distillate to produce mainly extra gasoline, and the hydrocracking unit, or DHC, to produce mainly diesel fuel and jet A1. At the end of the treatments, we obtained several bases ready to be blended to formulate the final commercial products. In conclusion, the third and last step of the refinery is to blend all the bases to obtain the final commercial products, complying with the specifications. It's during this operation of blending that the refiner adds biofuels like ETBE for gasoline and FAME for diesel fuel. Finally, I would like to thank you very much for having shared your time with me, learning more about crude oil refining. You should now be ready to use and practice all your knowledge by playing the following evaluation games. Goodbye to you all.